Hi, everyone. First of all, I want to thank you guys for being here tonight. The focus of tonight's presentation is essentially practical implications of AI in healthcare. And most importantly, how do you look at it from a systems engineering approach? Now, with that said, I want to introduce myself. I know Grant did have the aspect of it, but to give you a long story short, I work at Mount Sinai, and a lot of my job involves integrating AI and IoT technologies within our healthcare infrastructure. It also involves architecting our existing infrastructure and making sure it is functional 24/7. With that said, before this, I did work as an AI solutions architect on Dell's data science infrastructure team. So a lot of my job involved building AI systems for customers in multiple segments. With that said, healthcare and research were one of my biggest focus. So I took my knowledge from that job and essentially applying it at Mount Sinai today. Before this, I also did solutions engineering and corporate development. So my background is a mixed bag of engineering and business as a whole. Before we dive into this, kind of wanted to highlight one thing from the rise in agentic AI and the demand for healthcare's need for AI as a whole, right? When we look at healthcare, it's a very broad industry. We think about anywhere from diagnostics, which involves pathology or any other sectors as such, but it's not just that. It's also personalized medicine, administrative automation. Now, how does AI help in these kind of situations, right? So let's start with diagnostics, for instance. We have been able to utilize image classification to a point where we do not need doctors sitting with x-rays and polygraphs for hours and hours. Like, it can essentially detect heart patterns or your valve patterns where your blood vessels are contracting, let's say, over time. And these are some of the use cases that companies like Leighton Labs, Scribbly are trying to solve. And not just that, right? When we also think of hospitals and healthcare, it's not just the doctors that are playing a pivotal role in all of this. There are a lot of administrative problems that also everyday people face. Now, let me ask you guys, right? What has been, sir, if you don't mind, what has been your experience booking an appointment at a hospital or getting a scan or check done? Like a short answer, can you describe it? Will do. So, for instance, when you guys book an appointment, let's say even at a hospital, right? The point of time where you contact someone, fill out your electronic health records, to actually getting an appointment and sit with the doctor, that in itself is sometimes 2 weeks to a month process. And these are some of the problems that when we look at AI is trying to solve. With that said, how does systems engineering play a role into all this, right? We have been talking about AI, and honestly, everyone's using AI in every industry at this point. But how does systems engineering as a whole play a vital role in healthcare? So one of the things that are worth focusing on is healthcare is not the tech industry. We do not have software engineers specifically always working on these kind of problems. When we look at research in hospitals, yes, we do have a lot of people from STEM contributing to different costs. But then again, I, as a systems engineer, am not a doctor. I do not understand pathology as well as a doctor does. So when we approach healthcare, it is more of an interdisciplinary approach from a systems engineering standpoint, where we are working with doctors, clinicians, data scientists, machine learning engineers, and IT operations to make these systems actually come to life. Because when you look at a problem, right, you're trying to solve a problem. You're not just trying to build systems because you want a Ferrari, right? Everyone wants a Ferrari, but you need to know which track that Ferrari is going to race on. So these are the kind of intricacies the systems engineering approach solves. For instance, two industries that come on back of my head, right? Banking and healthcare. Very privatized in the sense of how it collects and keeps their data, because there's a lot of patient and customer sensitive data, electronic health records to credit card information, your social security, right? So as a solutions architect or an engineer, that's also something you take in consideration. How do you want to build it out? Do you want to build it out on-prem? If so, what data resides there? If you want to build it on off-prem, is it just the sales and marketing data? Last but the least, as you're building out these pipelines and working with data engineers, let's say, you also want to make sure they're encrypted in compliance with HIPAA. So if something does happen, your hospital is not getting essentially a court order of some sort, because those are also expensive. Few mistakes in these aspects can cost you millions of dollars in fines and fees down the line. So when we look at systems engineering as a whole in healthcare, it's essentially a bunch of scientists, engineers coming together to solve a problem. One of my goals today is, right, to all of us to come together and solve a problem, because I just don't want to talk about implications of AI. I also want to make this a collaborative approach per se, to actually for all of us to do something. So if you've ever been to a hospital, yes.
When we train a model, AI model, data is very important.
Absolutely.
Unfortunately, it's very expensive to get an EHR data set, and also in this country, it's kind of isolated. They don't have a nationwide EHR. For example, in California's data, it's different than Florida. You may get a Florida EHR, but you need another permission to get California's data. So how did you get this nationwide EHR? How much that cost you? Or even possible to get all those EHR across the country?
I do have an answer for you, sir. So I would say it is more case dependent at that point. For instance, if you work as a medical institution or a hospital, you already have access to that pre-existing data. But like you mentioned, right, it depends. If you have a startup and if you have the right amount of funding, that is a case that you'll have to make to your VC in terms of buying this EHR data. For instance, data isn't always free. Luckily, if you work at a research center or a research hospital, it's a lot easier for us to have access to that. Does that answer your question, sir?
Yes,
or
sounds good.
Okay, will do. With that said, I want to focus this slide on us actually solving a problem. So do you guys know what radiology is? Perfect. I found out what radiology is a year ago. So you guys are already ahead of me in that context. So today we are going to use a real life use case to solve a radiology driven problem. So let's say you are at a hospital that has a radiology center, which is taking around 7 to 8 customers a day, because these radiology systems that conduct your scans take some time. And one thing the hospital points out is that we are getting overbooked on appointments. We can only take 7 scans a day, but we want to move that. We are getting delayed scans, not fast results, which is also causing patient satisfaction scores to go down. So we want to make sure we are up to speed. Now, how are we going to solve that problem today? We're going to essentially work with an LLM model that not only uses image classification to scan these images and detect any problems or symptoms the customer has, but also simultaneously, let's say if throughout the day 15 scans are done throughout, it will prioritize the scans which have high likely symptom of a severe disease or virus involving into something. So we are going to build that essentially from a collaborative effort with systems engineers, architects, machine learning engineers, and doctors as a whole. Now, the outcome essentially that we're looking for is fast analysis times, making sure the results are out. And what I'm essentially trying to say is, if you are running a radiology system, we are trying to double your output and make sure the right patient is contacted on time so we don't have a mishap along the way. Now, to better explain this, right, I want to point out over here. So let's say you as a patient walk into a hospital and you're at either the front desk or you put an appointment to scheduling, right? Now, once you do that, the doctor or the nurse calls you into the radiology center where you're hooked to all these devices that are getting your scans ready, making sure they got all the electronic records to make the analysis needed. And once we get that data from these devices, it is moved through a system monitoring server to the data lake. Now, the system monitoring server over here is making sure that scans came out correctly in the first place. You don't want to put something for AI inferencing or churning, but not making sure if the bare results or bare data set, in this case, like you mentioned, is on point. So we guide it to a system monitoring environment into a data lake. And once that data or the images are stored in the data lake, we move it to a GPU server, or essentially an inferencing and ML operation server that conducts the LLM churning that it needs for us to get the results that we do. And once we get that, it moves it back into the data lake and provides it to the right doctors or physicians that need to contact that patient. Also, last but the least, as we're doing this, like from end to end, this has to be encrypted from industry standard perspective. So not only are we doing this entire process, we are essentially making sure this end-to-end process is encrypted from 0 to 1. Now, to simplify everything that I just said, right? That was a bit of a complex diagram per se. We're essentially using the imaging device at this point, putting that data into an inference engine, sending it to the department to make sure they get all the critical scans and know who to contact, and that's what we're trying to achieve. We're trying to achieve that today. Yes, sir.
So on this slide and the previous slide,
Yes.
could you use LLMs to reverse the arrows?
I'm sorry?
Could you use the LLMs or AI to reverse the arrow, to reverse data flow? Like you go back to the previous slide, for example, right?
Yes.
Like all that is what's happening now without AI. But if I wanted to use AI to actually like partially reconstruct a diagnosis with limited information, or a patient doesn't want an MRI, for example, a lot of MRI patients are a lot of MRI patients are claustrophobic, including myself, right? I
Yes.
don't get an MRI unless it's an absolute emergency. Just as an example, like it seems like you have all this data which a doctor wouldn't have. You could actually probably reverse what an outcome would be without having to do the whole top-down type thing.
I 100% agree with you, sir. The reason I made this more of a simple use case, so the entire audience here can understand it. I'm more than happy to discuss that with you after this presentation. Thank you. Long story short, we're building an AI system that can essentially give us an outcome of 32% faster triage, reduced times, and also make sure the results get to the right patients on time. We're essentially doing that, building a low latency network with HIPAA compliance to make sure as this data is going through different network controls, we have that intact. Now, quick question. How many of you guys like a little math over here? All right, not that many, but we are going to do a little bit of math today. I promise you it's going to be simple math. Now, before going into that, how are we achieving this outcome, right? By using an AI cluster. So when we talk about healthcare, banking, a lot of these AI clusters are built on-prem because of the sensitivity of that data. And to just give you guys a general and the sweetest definition possible, an AI cluster essentially is a custom mini data center which is specifically built out to churn advanced AI models to give you like certain outcomes. So the closest nature of models or infrastructure that has been built before for this is high performance computing. We just tweaked what HPC systems looked like back in the day a little bit, and then built it into an AI cluster which does exactly the same thing, just slightly differently, which we're going to go into in more detail. Now, let's build out this cluster, right? That is essentially the main part of the presentation tonight, because not only do I want to explain some of these problems, I want you to go through one of these problems yourself to understand how it works. So let's say we are working with an AI healthcare consulting company called Orion. And now this company, Orion, is essentially helping us build an LLM model, which is simultaneously taking 15 image scans Every image scan in this is around 2 gigabytes each. So the job that we're trying to complete over here is throughout the day, I want the system to take 15 scans simultaneously and deliver patients. So for instance, like I mentioned previously, our radiology center is only able to take 7 as of now. So it's not really meeting the demand. The patients are getting frustrated. And sometimes if some things are left unchecked for too long, you got problems. So we are trying to change that. And the best way I would love for you guys to approach this is as if you're building a gaming computer. This is one of the best ways I have been able to explain to my previous customers, and I think this would make a little bit more sense to you guys as well. So when I was little, one of the first things I built is my gaming desktop for playing Call of Duty. I looked at the back of the game and I realized, okay, these are the kind of requirements that I need. I need X amount of gigs of memory, X gigs of RAM, how much speed. And we're going to approach this problem in a similar manner, the same way we're building a desktop computer today. So for instance, after talking to Orion as a company, we find out that for us to compute from a processing standpoint, a single image, it's going to take 0.5 teraflops of speed. Now, with that said, we need 2 cores from a CPU standpoint for sequential processing, around 100 gigs of storage to actually make sure the software stack that Orion as a company is implementing in our environment to actually physically stay there. Last but the least, we want to make sure all this is happening really, really fast. So we want to make sure we have low latency networks, anywhere from 20 to 100 gigs at least minimum, to host this environment and give us the result as fast as possible. Now let's build it out. So I'm going to put the requirements over here so you guys can follow what I'm doing as we speak. So to start with building the cluster, we're doing simultaneously 15 images. So when you do 0.5 into 15, throughout the day, I need that AI cluster to at least give me 7.5 teraflops of speed for it to run 15 images, 2 gigabytes each. Now, when we do the similar math on the CPU core count, right, it gives us around 30, if I'm not wrong, from pre-processing standpoint. And if you've worked with servers, networking, we work in bits and pieces. So essentially 6, 18, 32, 64. So we're going to round that up to 64 over there. Now, from a RAM perspective, right, we have every single day 15 images being processed on temporary memory or random access memory. So when all this computation is happening in the background, this data is not always sitting in storage. It is being bought up from the storage level, and it is being computed using RAM. So that's why we need this, essentially around 30 gigs of memory. Plus, when you consider Orion's LLM models, the overhead that comes with that, we're looking at around 45 gigs. So we rounded up to around 64 gigs for future aspects and adding more workloads. And last but the least, right, calculating storage. I already mentioned the 100 gigs with Orion, but now we are saving around 30 gigabits of storage every single day. How? Because one image that you're storing per patient is around 2 gigabits. And I personally had never had to deal with a JPEG file or a PNG file 2 gigabits big. So this was also new for me while solving these kind of problems. So every day we're saving 30 gigabits per day. And we also want to make sure that we have a backup copy of this data, right? We don't want it just because one day our storage array or database goes off, we don't want our entire system to fail. So we are also mirroring that data for redundancy as we speak, and we're keeping 1 month retention backup. So when you do a total of that, you get around 1.1 terabytes worth of data in terms of storage standards. Now, once we have that, a single cluster for the minimum requirements that we're building out looks like that. However, one of the goals of this use case is we're trying to build something that is scalable over the next 5 years. Now, what I mean by that is, as of now, I'm building a system over here which can intake 15 images per day. But over the next 5 years, the hospital's goal is to build something that can take 30. So when I do the math over here, it's going to double over time. So we are also taking that into account as we're building these AI systems. Now, the full cluster over here essentially looks something like this. So I've doubled the cluster that we essentially try to build out. And for the next 5 years, 2x scalable, this is the kind of requirement you're looking for. Now, on the right side over here is essentially your AI cluster that I built out. Now, I'm going to guide you from a software stack as well as a hardware stack, what is happening, to give you guys a good understanding of how all this stuff is happening over here. So for instance, there you can look at EHR over here. So essentially, all that data that is coming from these radiology devices is going through system monitoring or management node. So essentially, from EHR to devices. And once that data has been recorded from a system monitoring standpoint, it is going into file storage. In this case, I have a background with Dell, so I understand that piece of hardware a lot better. However, if you have preferences with Lenovo, Nutanix, or any other competitors like Supermicro, you should go with them as well. We store the data in the storage node, then move that data, so essentially from the data lake to AI inferencing and running ML operations. So essentially, the data recorded is stored over here, and then it is moved down to the GPU compute nodes. Now, here's something that a lot of people don't tell you, which is essentially under the hood, right? We are using NVIDIA L40Ss as our GPU clusters. Now, why is that, right? Now, this is something I would say is a very industry-specific thing. For instance, when you're running AI, AI can be used for a lot of things, but you also need to know the kind of hardware you're running on. Now, if you followed NVIDIA or you own NVIDIA stock, I'm sure you've heard of H100s, A100s as the most popular GPUs in town. That is essentially the showrunner as of right now as we speak. But it doesn't solve the exact problem we're trying to solve. What those processors do is matrix multiplication, or good at matrix multiplication. So essentially, if you are a high-frequency trading firm or something that is taking a lot of binary data, that makes more sense. But the reason we're using L40Ss as a choice of GPU is they have what we like to call RT cores, which are essentially made for gaming, image classification. So when you look at a video game, right, in this case, that's exactly the kind of GPU cores that you need, even to play video games or do any kind of image classification. Now, once the data goes here, AI inferencing and ML operations do its work. It is again moved back to storage and then directly sent out as outcomes to the necessary doctors and clinicians to actually talk to their patients. Last but the least, these two over here, right? These are the networking switches. Everything that I talked from a systematic standpoint, this 1 to 10 gig management switch over here is sending these signals to make that happen. However, to get the result faster, or the churn time, right, for the LLM model or your AI model to spit out the result in 24 hours, not only do I need these GPUs to compute at 0.5 teraflops of speed, I need the right networking, which can push past 50 to at least give me 100 gigs of bandwidth speed for low latency channel. So as I'm doing all this in the background, I'm also making sure we have the network requirements needed. Now, here's the thing that I did not talk about, the HIPAA compliance piece, right? Building this thing out looks perfect, but also making sure you have the right vendors to supply you with the right encryption is also not necessary. For instance, personally, I would recommend if you ever want to build a high latency network, go with InfiniBand as a choice of vendor because they already have these encryptions in place for these networking cables to go through and through. So that is something I would personally recommend for you guys to go through. But long story short, this exactly does what this needs to do, and we have built that out in a scalable way that over time, this infrastructure is going to house 30 images per day. So that is essentially the goal. Now, a lot of this looks very hardware-y, very software-y, and looks very cool at the end of the day, right? But as a founder, or as someone who is running an operation in the backyard, what does it look like from an expense standpoint, which is also an important piece because we all think about building these models, but two things we do not consider, which is speed to delivery, which is the first aspect. How fast do you need the result? And how big of a model do you need to compute that kind of electricity? So speed and power are one of your biggest allies when it comes to this. With that said, going to go a little bit on that side of the drill down. Now, I know we've talked about building these kind of infrastructure environments out, but what does it look like? For instance, the previous slide over here, right? You see all this hardware over here? This in itself essentially would cost you around $74,000. It's like buying a Ferrari on your first try, but you never did the math of the gas, the kind of insurance, and those things that you're going to need to solve these problems. So that's where, if you were to run even a small AI cluster like that, you're at least spending $16,000 on average to keep that alive throughout the year. On top of it, if you have worked in tech, you know everything requires licensing. Anywhere from using the NVIDIA's CUDA environment to deploying a Windows server, for your Microsoft environment to have database licensing, that as a cost as a whole comes around $10,000. So from a leadership standpoint, not only are you looking to deploy this, but also justify this to your CTO or your CFO. So, hey, we're starting this radiology program. We want to double the churn of our customers. But you need to be able to explain these kind of results at the end of the day. So if we are looking at an outcome of around 300K over the next 5 years, so let's say we do plan on expanding a GPU year 3 and year 5, right? One GPU would at least cost us $7,500 at this point. So when you do the math of just the infrastructure, 89K. Power and cooling, 100K. Licensing in itself, around 70K. So the whole cost analysis of this, you're spending over 300K. So one thing that you want to take in consideration as you're expanding your radiology center and the amount of customers or patients you're taking in, that the insurance, the clinicians, everyone is not only getting paid, but we're also bringing revenue in. Because hospitals and research centers can be a nonprofit business, but then again, it is still a business. We have to pay all these emergency professionals out. So to economies of scale, essentially, you got to justify this to your CEO or CTO at the end of the day. So these are also the aspects of AI systems project management you need to deliver. Now, this is just one example that I gave you. Yes, sir.
Yeah, if you're looking at this in isolation, but if there are other AI issues going in on the hospital, you think a long-term strategy.
I do have some.
You're going to end up building a data center inside your hospital.
I do have something to round that up. So I'm glad you brought that. So when we look at the bigger picture as a whole, I just brought up one little problem the hospital is solving. Now, especially in a medical environment, we are trying to break down proteins using generative AI to all the way essentially optimizing your administrative paperwork, making sure physician scheduling and a lot of these elements are also being optimized. So when we have hundreds and thousands of workloads like these going at a data center, this is what enterprise-grade systems design looks like. With that said, I want to show that one example to kind of from a multiplying effect. And when you're running an enterprise business, these are the kind of the connectivity you'd need. 400 gigs of speed, making sure you have the right licensing. This essentially would cost you at least $3 million just to run all these operations. Now, I want to wrap up this presentation and make sure that everyone had a little bit more understanding today of AI in healthcare than they did an hour ago. And thank you so much for your time, guys. I will open the floor for any questions and concerns that you guys have.
Amazing. If anyone has any questions, feel free to line up over here. We'll just give you the microphone. Or actually, here. Let's do this.
Yeah, I think for the AI models or the outcomes, we care about the speed, how fast they can go, and also the speed. One sense care about in the healthcare also there's performance, precisely record F1A, those kind of stuff, or it's been actually how this model works in as a diagnosis.
I love that question actually.
Percentage.
I love that question because this is something most people really don't talk about while building this. So as an AI solutions architect, this is one of the bigger questions that I came across is, what are you prioritizing while solving this problem? First thing in this case would be accuracy. Second is time to value. Third thing is, are you using an in-house model to which you've fed the data, or you're using a third-party model? So these are, depending on every use case, you take into consideration. For instance, for you to solve a sales and marketing campaign, you do not need a 64 parameter AI model. You can use a 4 billion parameter model from your phone altogether. So to answer sweet and short, if your use case relies on accuracy, then you might have to actually talk about timing with your customer. Hey, if this is the kind of accuracy you're looking for, this cannot be completed maybe within a day or an hour. It might take you more than 5 days to do that. So depending on your business logic and priority, these are things that you take into account. You can always find third-party models on Hugging Face, which is a platform that has a library of AI models, or you can build one out your own. Mostly in healthcare, we do use some third-party, but a lot of them are in-house and developed because patient lives are a little bit, they're too much to trust a random model on the internet. Does that answer that?
Yes, thank you.
Will do. Anyone else? Yes, sir.
Eric, thank you for coming. Here you go.
So from a healthcare perspective, most of the time, these programs are actually happening internally because of access to the data, infrastructure, and so there's not a lot of opportunity for external innovation at most of these centers, right? Because they have
I agree.
Unique solutions are kind of unique to that specific medical center. How are you guys approaching that from an ecosystem standpoint and actually allowing third-party vendors in to solve some of these problems?
So one thing about Miami is that, and this is something I found out through my professional experiences myself, being on a few contracts with some other universities down over here, is there are at least 5 to 10 universities over here that share a part of their patient data, not by the name and obviously leaving some critical elements out. We actually share, let's say, hospitals like or part of FIU or Mount Sinai and Baptist. They actually have a very friendly ecosystem where they utilize each other as partners to share that data. From an XYZ level, obviously there are certain parts of that data that you do not want to provide, like exact specific customer. For instance, Mount Sinai services LeBron James, but I don't want LeBron's data roaming around 5 different hospitals. So that deal helps us get that kind of data in 5x quantities. So I would say it's dependent on the hospital or the research that is being funded.
Yeah, I mean, like what you were mentioning is a lot around quality process improvement, more patients to the door, better care, optimizing it. So usually that's very, very targeted to that specific, to that specific entity. And it doesn't, obviously there's some problems that scale across multiple other networks, but usually it's network specific. And so, just curious.
I would say on research purposes, I've talked to, and this is in my previous job actually, I talked to like a few researchers regarding solving a gene editing problem. And the way I understood down over here is there are 3 universities that are sharing that specific data, which they got access to by putting in the right forms in places. So I would say it's a hard process at that point, specifically if a university or a hospital is trying to solve a very specific problem that is very in-house medical center. Another way I would approach it, and this is something, is a non-reliable approach, right? Worst case, out of desperation, at the end of the day, you can always go and buy some of that data, like this gentleman mentioned over here. But that would be my last approach to it. If you can get in-house and you're working in the institution where the data has already been recorded or produced, you're in luck.
Amazing, amazing. Well, thank you so much, Shivv, for an amazing presentation. Everyone,
Thank you.